What is a cloud inversion? Well, over my years of hiking and photographing vistas across the best regions of the UK, the most memorable moments have been when I've been stood high above the landscape, waiting for the sun to rise as the valley below slowly fills with mist in what is known as a cloud inversion. And I can't lie, it's hard not to feel a little smug knowing everyone else is fast asleep or down below thinking it's a damp and misty day. Now, cloud inversions are, in my opinion, one of the best spectacles to witness as a hiker, a photographer, or whatever has you out in the hills. In principle, the phenomena occurs when you get a perfect concoction of high humidity and clear skies, allowing temperature drops through the night. Sounds simple, right? Well, they can be quite elusive still, and they're governed by a number of factors. But with a good understanding of how they form and what to look for in the weather forecast, you can increase your chances of success quite drastically. And don't also forget about other opportunities a good inversion brings. Beneath the inversion, as I say, it's damp and misty or foggy, and this is a perfect chance to photograph woodland. Now, the phrase cloud inversion is actually a nickname. The correct terminology of what you're witnessing is a temperature inversion. Now, the standard meteorological profile is that temperature reduces with height. And this is generally about 2 degrees Celsius for every 300 meters of elevation. Whereas during a temperature inversion, it actually gets warmer as you go up to a point, with cold air down at ground level due to it being more dense than the warmer air. A telltale sign of a temperature inversion to look out for is smoke rising from a chimney, because it'll rise to a level and then plateau off horizontally. So how does this profile form? Well, during the day, the sun emits solar radiation that is absorbed by the ground. But by late afternoon, there is more radiation being released from the ground back to space than there is being received. When clouds are present, the radiation emitted by the clouds or ground is similarly reabsorbed by them, preventing rapid temperature drops. When the sky is clear, the ground rapidly cools, and similarly the air above the ground too, causing an increase in air density, which is why the cooler, denser air drops into the valleys. As the air cools, it can hold less moisture and results in water vapour getting forced out in the form of liquid droplets or mist. Where clouds are present, nearly all the radiation emitted is absorbed by the cloud, insulating the air beneath and preventing the ground from cooling and the profile occurring at all. Ventasky is a fantastic app for checking whether or not an inversion profile is predicted. The temperature overlay in the app or on the website allows you to look at temperature at different elevations. An example of what to look for would be an increasing temperature from ground level and then a sudden drop, for example between 500 meters and 1500 meters above ground level. Usually on Ventasky you can see a rise up to say 750 meters, and then when you select the 1000 meter tab, the temperature has reduced. You want to look for a temperature inversion at an elevation lower than you intend to be, so you have that body of cold air below you. To put that into perspective, the highest peaks in the three nations of Great Britain are Ben Nevis at 1345 metres, Snowdon at 1085 metres, and Scafell Pike at 964 metres. So to recap, a temperature inversion is created by the ground being able to cool rapidly during a clear night. The air above it cools also and becomes denser, causing it to fall into the valleys. And you can check these temperatures at different elevations on Ventasky and use any of these apps to check if you're going to have a clear night and morning in the first place. In order for the mist or fog to form in the inversion, then the air has to be full of water vapour. This is seen as humidity on the weather apps. The air holds less water vapour when it is cold, so as it reduces in temperature, the water vapour is forced out of it in the form of liquid droplets or mist and fog. Dew point is a key consideration when it comes to the formation of temperature inversions. Without it, mist cannot form. As temperature drops, the amount of water vapour in the air that it can hold reduces. The dew point is the critical temperature at which the air must be cooled to, at which the air cannot hold any more moisture in gas form, and if it were to cool any more, then water vapour will be forced to come out into the atmosphere as mist, fog or dew condensing on the ground. It's the same principle we've already discussed in which clouds form. Now, because convection through the air is quite slow, you will always see dew or frost, if it's cold enough, forming on the ground before any mist or fog in the air above it. And it's worth noting here that the difference between fog and mist is simply the range of visibility, where if you can see less than 1,000 meters, it's dense enough to be called fog, and further than this it would become mist. So you'll probably hear me interchangeably using those terms throughout this course. To put dew into further context, if you're witnessing a cloud inversion, the top of the fog is actually the dew point temperature line. Dew point is also important when it comes to frost. Now, there are two types of frost, deposited or freezing. We get deposited frost like hoarfrost, that covers pretty much everything when the dew point is below freezing, as it causes water vapour to transition directly into solid state like ice crystals. This type of frost generally gives that winter wonderland look, as it forms the perfect frozen crystals that reflect light. Here's a photo I captured in the Lake District earlier this winter, where dew was deposited directly as frost across the whole landscape, including otherwise bare-looking trees, and transforming this into something quite spectacular. You'll also note the mist behind the trees. This was part of an inversion from further down the valley. Frost formed through freezing of water droplets or dew does not have the same effect as this, as it's formed when dew is condensed onto the ground and then subsequently the temperature has dropped, causing it to freeze. Here is an example of rime frost deposited on some rocks I photographed high in the clouds on top of a mountain in Snowdonia. This type of frost is first a liquid and then freezes, attaching itself to the surface. You might notice that on the weather forecast, the temperature suddenly drops before sunrise, which can cause freezing dew or deposited frost, depending on how much condensation has already occurred. And you may have actually experienced this when you're actually out, as you suddenly reach for your woolly hat, or in my case, my beard freezes. Bringing it back to inversions, this temperature drop actually amplifies an inversion as the air cools rapidly and water vapour is forced into condensation. This is why, if you've ever seen an inversion, the fog swells significantly at sunrise. Here's some footage from Loughrig Fell in the Lake District taken last autumn. Now, as the sun rose and the inversion swelled significantly across the landscape and slowly worked its way up the valley and across the scene. You can actually see the swelling happening here with this time-lapse footage taken at Winnett's Pass in the Peak District. So we now understand why the inversions swell. This temperature drop causes the water vapour to be forced out of the air as condensation or water droplets. But what causes the temperature drop at sunrise in the first place? Now remember this from earlier in the course. Change in temperature creates change in pressure, which creates wind, and winds move from high pressure to low pressure. So, as the sun rises to the east of you, it starts to heat the air above the ground, and as we know already, the warmer air here rises, creating an area of low pressure. Meanwhile, where there is no sun yet at all, it's still cold and dense in an area of high pressure. Therefore, the changes in temperature create winds, which bring fresh, colder air towards you. I therefore would always recommend you getting to your chosen location at least an hour before sunrise, as any later the show's already begun and you could find yourself shrouded in mist or fog once the sun has risen and lose any opportunity to get higher than the inversion below. Apps like Clear Outside give a visual breakdown by hour of various parameters. In general, what to look for would be humidity higher than 90%, and with temperature dropping to the dew point through the night and particularly in the hours leading up to sunrise. As the temperature drops, this will force the moisture out of the humid air, forming the mist and fog of the inversion. It's also important to consider wind speed. Wind speeds increase from zero at ground level and exponentially with height. Now, turbulent wind flow is created near the Earth's surface as the wind hits obstructions and unevenness, creating a mixing of faster moving air from greater heights with slow moving air close to the ground. Therefore, for cloud inversions, in general, the less wind the better. However, it is possible that gentle breezes can supply a forming inversion with moisture. And in my experience, anything less than 5 miles per hour is generally ideal. Although I have witnessed inversions form in winds way in excess of this, provided the inversion profile is strong enough. High pressure can be a good sign for cloud inversions also, as these weather patterns are associated with prolonged periods of stable weather, including low winds. Although it may seem somewhat obvious, you do generally get more inversions over bodies of water, and a lot of this is due to them being in the bottom of valleys where we know cold, denser air sinks to, and then moisture condenses from water vapour into fog. However, there is more going on. You'll notice even on mornings where we don't have cloud inversions, that when it's calm and cold, you can get mist forming just above the lake's surface. If you recall, water has very high specific heat capacity, so it takes longer to cool down in autumn and winter compared to the air and ground around it. We already know that on cold nights, heat is lost into space. However, due to convection, colder air does naturally drift over to large bodies of water where it's warmer. Remember, change in temperature creates change in pressure, which creates winds, and winds move from high pressure to low pressure. It's the same principle and is similar to the convection that makes the temperature drop just before sunrise. It's also worth noting that if you are photographing calm water reflections with the morning mist, that as soon as the sun starts to rise, these breezes can quite suddenly ruin your reflections as the breezes start to ripple the water's surface. Now, because the water is warmer, there is a very thin layer of warmer air just above the body of water, and a small amount of the lake evaporates into it. And when the cooler body of air from the land meets it, condensation forms. This is why you generally see this spectacle on autumn and winter mornings, when the nights are longer and the air cools more. On our weather apps, we'd want to look for clear nights with as little to no cloud as possible. This allows the air to radiate out to space and cool. Little to no wind is ideal also, but I'd suggest anything in the region of 2 to 4 miles per hour, as some bodies of water can be more sheltered than you think due to the surrounding topography. So it's worth bearing this in mind too. To recap, clear nights allow the ground to cool. This subsequently cools the air above the ground, creating an inversion to the standard temperature profile, meaning it actually gets warmer with elevation, to a point. Now, provided there is adequate moisture in the air, this cooling process increases the density of the air and forces invisible water vapour out in the form of liquid droplets, which form dew, frost, mist and fog. Combined with our temperature inversion profile, this can create a blanket of cloud close to the ground that fills the valleys, because all this colder, denser air has sunk to the bottom. Now, the dew point is the temperature at which the air must cool before the air reaches 100% relative humidity, or simply, at this point, moisture is forced out of the air. And you can check humidity and dew point on your weather apps. Now, inversions can be somewhat seasonal. Generally, I find autumn is best, particularly in combination with autumn colours. But they're also possible through winter, occasionally in spring and summer also. This is because we need that larger change in temperature, and particularly during the summer months, the nights just aren't cold enough, or even long enough to allow the ground radiation to escape. But that's not to say they can't ever happen. I've witnessed inversions all through the year, but they can just at times be much less of a spectacle or less intense. Now, September and November I find have very strong inversions, as we start to have longer and colder nights, yet the days can still be quite warm. Sometimes these inversions can be so strong that you simply can't get high enough and you'll become shrouded in fog. And you can check the level of the top of the inversion profile on Ventasky. But remember, the temperature increases with height to a point. at which point it then decreases with height. So remember to toggle between the layers on the apps in order to spot this. And this is, however, just an indication on height, so I would advise having a backup plan. Maybe somewhere you can go in the fog, or pick a mountain where you have the option to keep going higher to get above the cloud inversion. So keep your eye on the weather, and good luck, you won't regret it.